Okay, good morning. Happy Monday. Today is class number 17. We are going to cover exponential derivatives. Recall on our last class, we reviewed some stuff about exponential functions, and we have a pretty good guess as to what the derivative of e to the x is. We'll see it officially today. Coming up later this week, we've got a review of trig functions back in chapter 1. There's no calculus there. That's just pre-calculus stuff. And then on Friday's class, is that right? No. Friday's class is our project check-in day, and then Monday next week we'll do derivatives of the trig functions that we're reviewing. All right, so Friday coming up is our project check-in day. Also on Friday, I will hand you quiz number 2. You'll take it over the weekend and give it back to me on Monday. Questions on the calendar? Okay, so on page 19, we'll start up here at the top with our summary. Today we discover formulas for the derivatives of exponential functions and use them with other derivative rules like product rule, quotient rule, chain rule to solve optimization problems. These optimization problems, despite how much you don't like them, are not going away. They're going to be a thread through the semester. When we see new derivative rules, we get to do new kinds of optimization problems. Okay, so number 1, can we apply the power rule to find the derivative of e to the x? So it is quite tempting to say, oh, I can bring the power down, copy the e, and then new power, x minus 1, right? That's the power rule. Bring the thing down, subtract 1 from the power. Can we apply the power rule to e to the x? No, power rule is good for x to a number, not e to a variable. So this is a big no. Don't do that. But in number 2, recall from the group activities last class, we conjectured a formula for the derivative of f of x equals e to the x based on its graph shown below. And so what you did is you drew some tangent lines. Let's pick a different color here. You drew some tangent lines and you plotted some points on the derivative. And what did you discover when you graphed the derivative? Sure seemed like the graph was very similar to e to the x. We can't know that it's exactly e to the x by just drawing a picture, but it sure felt like it was close to e to the x, and it turns out it is exactly e to the x. So here's a sketchpad demonstration that will hopefully further confirm. So the red here is the graph of e to the x, and the tangent line at this point has a slope of 1, and 1 happens to be exactly the y coordinate of that point right there. Okay, that's fine. And then I'm going to hit this button to move it to x equals 1 or very close to 1. The slope of that tangent line, 2.7180. The y coordinate at this point, you can read it right here, 2.7180. I'll go up to x equals 2. Slope of the tangent line is 7.3876. What's the y value there? 7.3876. And the same thing works over on the left-hand side of the y-axis. The slope of the tangent line is 0.3679, and the y value at that spot is 0.3679. And so it turns out that the derivative of e to the x is e to the x. And it's proven in your book. You can take a look at it later if you're interested. But this is surprising. And I don't often bring religion into a math class, but there's something miraculous happening where the derivative of that function is exactly the same as the y value at every single point. Right? The derivative, the slope of the tangent line perfectly matches the y value at every point. Okay, so let's. Yeah, but I can't show you where. All right. Okay, so somebody was asking a question about any other. Great question. All right, so let's fill in our blank here and then we'll answer Levi's question. The derivative of e to the x is e to the x. Derivative of e to the x is e to the x. Can anybody name another function where the derivative of the thing is exactly equal to the thing? We don't know the derivative of natural log yet, but it's a good guess. Turns out the derivative of natural log is not the natural log. 0. What's the derivative of 0? 0. So you haven't found us an example, right? All right, maybe that one's not as miraculous as the e to the x one, but it still works. Any other examples? Did somebody say infinity? What's the derivative? All right, so I'm going to erase that because as a math guy, I don't like writing infinity as a number. But if it were a number, what would its derivative be? I mean, if it's a number, its derivative is 0, right? So, okay, so all right, so we're gonna get rid of that guy. That's not quite fitting the bill. There actually are infinitely many other answers that we can put in here where the derivative perfectly matches the output, but they all look like e to the x. Can I tweak e to the x in some way, like a controlled tweaking? But yeah, but x is a variable. How can I tweak this so that the answer stays exactly the same? Like what if I added a number to it? Like 7 plus? What's the derivative? Is it 7 plus e to the x? It's just e to the x, right? So that 7 would disappear. I need to put something in here that isn't going to disappear, but is also not going to change. Josh? What's the derivative of 7 times e to the x? Is 7 e to the x, right? We know that constant multiples stay. So there's another example of a function whose derivative doesn't change. And in fact, those are the only functions where the derivative is exactly equal to the function itself, is some number times e to the x. And in fact, even Stephen's example with the 0 is 0 e to the x, right? So those are the only functions out there where the derivative is the function itself. Great question. Okay, let's fill in derivative of e to the stuff. This is our chain rule now. So we follow the basic derivative rule. E to the x becomes e to the x. E to the stuff becomes e to the stuff. That's certainly the first thing we should write. But then we remember the chain rule says times derivative of the stuff. Okay, it's a brand new rule for us. Okay, let's take a look at number 5. So we just saw our easiest derivative rule ever for e to the x. Turns out it's not too hard to differentiate any exponential function, not just e, but any base to the x. So here's our brand new rule for any other number, this guy right here. Derivative of a to the x, where a is some constant, is, I'm going to cover this part up, a to the x. Well, that looks quite similar to what we just saw up above, right? E to the x becomes e to the x, a to the x becomes a to the x. But in general, you have to multiply. Maybe we'll put a little dot in here to be clear. We are multiplying by ln of a. Whatever the base is, you got to multiply by ln of that number. Okay?
This works for when a is constant?
Yeah, a is a constant. So for example, what's the derivative of 5 to the x? 5 to the x, ln of 5. That's it. Okay? Do you see that e to the x is a special case of that rule? Right? Because it would be e to the x times what? ln of e, which is 1. One of the reasons that we really like e to the x in calculus class is that you don't have to multiply by this ln. I mean, you do, but it's just a 1. Okay, and so then we can fill in the blank with another chain rule thing here. Derivative of a to the stuff. Copy our basic rule from over there. What is it? A to the stuff times ln of a. That's the whole basic rule, always, but then times the derivative of the stuff. There's the chain rule coming in. Okay, so we're going to try one last derivative problem together here before the activities. This thing in the brackets, which is on your paper, was far too simple, so we're changing it to something much more complicated. Can you cross it off and write what I've got here? We're going to do the derivative of e to the 4x squared minus 7x times 2 to the e to the x. Okay, first and foremost, I see e to something, I see 2 to something, but what do I see before I see either of those things? Is multiplication. So what rule? Product rule. We got to do a product rule. That's going to guide us. Okay, let's do our product rule. That thing up there equals. Okay, for me, the product rule says copy the first, multiply by the derivative of the second. So we copy the first, e to the 4x squared minus 7x times. Now we're doing the derivative of the second. I'm actually going to underline. So the first is in blue, and the second is underlined in purple. Okay, so the derivative of the second, derivative of 2 to some stuff. We just saw up here in green, derivative of a number to some stuff. So we're following our green rule here. What are we doing? 2 to the e to the x, that's copying the a to the stuff. A is the 2 in this case. Next thing, ln of 2. Let's see where we are. And then times the derivative of the stuff. What's the stuff in this purple? Is e to the x. So now we have to do a brand new derivative of e to the x. What is the derivative of e to the x? Is e to the x. Yeah, the 4x squared stuff, we haven't taken its derivative yet, but we're getting to that piece. The product rule hasn't told us to take its derivative yet. So what we just did was I'll underline in blue. We copied the first times the derivative of the second. All of this stuff expanding out was the derivative of the purple thing from above. But then continuing the product rule, what's the next symbol? Plus, and then we'll do second times derivative of the first. So we're copying the second. That's 2 to the e to the x times the derivative of the first. Now we're finally looking at what Ben had mentioned. I'm looking for the derivative of e to the 4x squared minus 7x. That is an e to the stuff. So what do? E to the stuff, e to the 4x squared minus 7x. Yeah, you could do times ln of e times 1, which would be okay. I'm not going to write that. Times the derivative of the stuff. The stuff for this blue is the 4x squared minus 7x. So that's the derivative that Ben was waiting for. It's right there. I'm missing something. What are we missing? Oh, yeah, I think I'm okay here. The equal sign, yeah. But you could put a dy dx in the front. That 8x minus 7 needs to be in parentheses. At the moment, it looks like I'm only multiplying by 8x, and then after I do that whole multiplication, I subtract 7 at the end, but that's not right. Just like that is good. And I'll underline that whole thing in blue. It came from the original thing underlined in blue. Okay, so the calculus is done. We're just going to do one simplification step here, one algebraic step. It looks like a big mess. It's not really going to get all that much better. But if we had to set it equal to 0, then factoring this whole thing would be useful to us, right? Because if you have an equation where there's a 0 on one side, if the other side is factored, you can write down simpler equations. So we're just going to factor out the greatest common factor from both terms. There's only 2 terms up here, separated by the big plus sign in the middle. So what do we see that's an exact carbon copy in this first term and also the second term? We see e to the x. Do we see that over there? Wait, is there an e to the x in both? Actually, there's not. I see 2 to the e to the x. That's the same. E to the 4x squared minus 7x is the same. Both of those are coming out in the front. E to the 4x squared minus 7x times 2 to the e to the x. And then we'll put big square brackets. Okay, so in this first term, in front of the plus sign, e to the 4x squared minus 7x is out. 2 to the e to the x is out. So all that's left is ln of 2 times e to the x. What's the next symbol? Plus, now we're at the second half here. So I'm going to check off 2e to the x. That's out already. e to the 4x squared minus 7x. That's also out front. So all that's left is this 8x minus 7. Yeah, it's all multiplication. Yeah, I mean, I would probably write it in parentheses once and then recognize that it didn't need it anymore. The reason it needs it here is that it's physically all attached to a multiplication, but now it's just addition, or a 1 times, because everything else that it was attached to has been pulled outside. So I think that's it. We can't go any farther than that. But factored form, like I said, is helpful because we've got so many equations equal to 0 in this class. Ben. 2e2. Oh, the factoring? I think we're okay with just one. Let me put something up here. Like if we had 2 of them. So what can we factor out? Put a plus sign here. What can we factor out of both x? And so when you pull x out, is there a 2x or is it just x? Right? Yeah, so I think we're okay. Other questions? Okay, the activities start on the next page. I'll just give you a quick heads up. This first page is sort of standard, like very brief, unrelated to each other activity type problems. But on the page after this one starts a fairly long activity that actually used to be a full-fledged project here in this class. And so you're going to read a long collection of problems all related to this thing called the surge function. Let's see if we can get all the way through.